The energy separation between a bonding and an antibonding orbital is going to depend on the extent to which the atomic orbitals overlap. A bigger overlap is going to imply a bigger energy separation between the bonding and antibonding. So if you look at the molecular orbitals from a 1s overlap versus 2s overlaps, you can see kind of the following situation happen. One s orbitals are very small, and that means that when you bring the nuclei of something containing a 1s orbital close together, you're going to get a fairly small amount of overlap before the repulsions from the nuclei start to matter. So you end up with a reasonably small energy separation. Because the 2s orbitals are bigger, you typically get more of that orbital overlap, and that implies a bigger separation of the molecular orbitals. As you move on to more complicated systems, you're going to encounter atoms with more atomic orbitals, and you're going to encounter heteronuclear systems, so systems that have different types of atoms involved. And that means that the starting energies of your atomic orbitals are all going to be slightly different. What will happen is that the molecular orbital diagrams are going to become just an awful mess. They'll become very, very complicated. And that becomes especially true when you consider that we've only talked about interactions between s orbitals and s orbitals, or p orbitals and p orbitals. But in reality, you can have interactions between s and p orbitals. And eventually, some d orbital interaction is going to become relevant as well. So, we're going to look at the relatively simple second row homonuclear diatomic molecules. We'll look at these because they're homonuclear, and that means that the atomic orbitals on either side of that molecular orbital diagram will be starting at the same energy, and that will keep the complexity to a minimum. The 2s orbital on each atom doesn't just interact with the 2s orbital on the other atom, it can also interact with the 2p orbital on the other atom. And the size or intensity of that 2s to 2p interaction can actually change the energy position of the molecular orbitals. So I'm going to draw the molecular orbital diagrams that are going to be representative for a large interaction and a small interaction. So I've drawn the 1s, the 2s, and the 2p orbitals for each of the atoms, and now I'll draw the molecular orbitals that result. So far, this looks, or should look, like the molecular orbital diagrams that we've drawn already, just a little bit more complicated. Now, this is for a 2s to 2p interaction that's fairly large, and I haven't shown it with the dotted lines just for the sake of limiting the complexity. For a small 2s to 2p interaction, you're going to get a slightly different structure. The sigma 1s and sigma 2s molecular orbitals look pretty much identical in structure. The difference is going to show up in the energy ordering of the 2p molecular orbitals. With a small interaction, now the sigma 2p orbital is lower in energy than the pi 2p, and the sigma star 2p is higher in energy than the pi star 2p. And this is for second row elements, so fairly small, fairly limited in terms of number of orbitals and number of electrons. And it's for homonuclear diatomic molecules, so same atoms involved, not very many atoms involved, very simple systems, and yet even this has a ridiculous amount of complexity. And it only gets more complicated as you start adding more atoms, more electrons, and that kind of thing.